Hello guys, today we will discuss microprogramming in terms of digital circuits and ASM and digital circuit design. So it's very different from the microprogramming of the Arduino and the Raspberry Pi. Even though we write microcode for them, it's quite different. It's MicroPython and it's different. Okay, so in ASM charts, what is microprogramming? So it's about programming the programming the state table, programming the state table. Now you'll say, well, how can we program? What does it mean to program a state table? Actually, uh, how generally how do we if we have an ASM, how do you design the circuit for this ASM? Well, you have different methods, right? You have mux implementation, you have one hot mux implementation, a different you have various implementations, and you have ROM implementation. Okay, in which you assign the state tables and the state variables directly to the ROM. Like you have them stored in the memory, and you can just access them without any computation. So microprogramming is based around this implementation, ROM implementation. So how can you implement this in ROM? And you, micro here means you have to reduce the state table, reduction, right? For example, let's say we have this ASM right here, right? We have this ASM right here. So we'll take this as an example. Let's say we have state P, it gives output O1, and we have taken the address variables A and B. This would generally go in the flip-flop. So the state variables, so A and B, because here for P we have it 0 0, Q 0 1, R 1 0, and S 1 1, and we have X and Y as the variables, as the we say them qualifiers. Why the qualifiers? Because they are the variables, the decision variables, you can say. So how would you write the state table for this? Of course, we'll have on the input side X and Y. We'll have A and B, which would determine the state, current state. The output would be, what would be the output? The next state that will be determined by A dash and B dash. Okay. The X and Y would be determined by the remaining circuit, right? We are just thinking about the states. So A dash and B dash and the outputs, right? The X and Y will be determined by the outputs. We won't write them here. We can implement that in a combinational circuit, extra combinational circuit. So I can write output, just output. I'll consider generally it will be written as output 1, output 2, and output 3. Which one of them is true? But I'll write just output to decrease the uh, to increase the clarity. Okay. So and I'll also add one current state. Okay, current state. I'll write here the alphabetical state. So let's say the current state is P. Current state is P. Then it depends on X, right? We will go here. It depends on X, right? But is it dependent on Y? No. So Y here will be don't care. So I can write X for the don't care, but to reduce confusion I'll write phi. Okay, y is here is don't care, and X is either true or false. I'll and I'll say, let's say take the false one first. Let's say it's 0 for A and B. A and B are 0 here. Okay, so what will be A dash and B dash if X is 0 and Y is don't care? So Y is absolutely don't care. If X is 0, we go back to P again. So A and B are again 0, and output will be O1 because we are at P state. We are in P state. Again, we have one more condition for P state. If X is 1 here, this means X is true. We jump to Q state, right? So Y again here is don't care. A and B initially were 0 0. The next A dash and B dash would be 0 1, right? And O will be the initial one, O1, right? Because we are the current state is P, right? So the current output will be O1. So just like finishing this, we go here, next state Q. Okay, so Q, A and B first I'll fill, it's 0 1, and as you can see both X and Y here are don't care. We directly jump to R no matter what. So we directly jump to R, so this both are don't cares. Directly jump to R is 1 0, and output will be O2, right? So this is done here. For O3, for R, in R it is 1 0, A and B are 1 0. We have two choices for Y, and X here is don't care. X is don't care, and again I'll write X is don't care. We are at 1 0. Two choices for Y. Let's take false first, true next, right? So false first, true next. What is the next state for R? If it's false, Y is false, next state for R is S. It will be 1 1, and output would be O3. If it's true, Y is true, we go back to state 2, state Q, and it will be 0 1 0. Next state would be Q1, right? Q, and it will be 0 1 A dash B dash, and output will be O3 again. And for the S, both X and Y are don't care, and A and B as 1 1 initially. Next we have A dash and B dash, that is 0 0, and output is O3. Okay, cool. So how do you implement this design? How do you implement this design? We have this. If we are talking about ROM implement, so we'll have a PROM here. Let's say we have a PROM here. Okay, what is the next thing? It will take input as A and B, the current addresses, right? A and B. Let's say we give them A and B, and it gives us back. What does it give us back? And it takes input as X and Y, more inputs X and Y, because these are the input variables, these are the output variables, right? So we'll give X and Y, X. So we'll get our output as A dash and B dash, of course the next states, A dash, B dash, next states, and the outputs, right? 1 2 3, O1 O2 O3. I'll just call them O. Okay, we'll get this output. We'll take this as bus. Now we have two state variables, right? So we will have two flip-flops here. flip flop 1, flip flop 2. One will take A, one will take B. They will store the outputs and then, as usual, they'll go give it back here, right? And X and Y and this outputs. Okay, this will go to some combinational logic, and this will produce the next X and Y. Okay, combination. This will be our entire design for the circuit using PROM. But now, as you can see, how many gates are we using? How many storages we are using? Because this is don't care situation here. Because it is don't care, we have to uh, write for its value 0 and 1 here in the address line. This would be the address line, right? This is the address line right here. So let's do this. For this address line, for both of the values for y, for x0, if x is 0 and a and b are 0 0, all of them are 0 for both values of y, 1 and 0. For both of them, we have to put the same 0 0 and output 1 here. We have to program it in such a way that both of them will be equal. Like both of them should be equal to this set of values right here. Okay, so we have to implement it like this. So there are 1, 2, 3 and 4 bit address line. Okay, we have 4-bit address line, right? So 4-bit address line, and the output is 1 2, and this is O1 O2 O3 5. Output is 5-bit for 4-bit address line, and 5-bit we have 5-bit output. 4-bit address lines are 2 power 4 addresses, right? 2 power 4 addresses. That means for 16 addresses we have 5-bit output, means multiplied by 5 we have 80 bits. It doesn't look like much, but for a small circuit like this is huge. Because for it's easier to keep less address lines, right? So because, and this is also hectic, very hectic, because you have to program all the 16 lines differently, all the 16 addresses you have to program it 16 times, right? You have to program it 16 times. Then how can we reduce it? So that's where microprogramming comes in. There are two types of microprograms. One is mux based microprogram, and another one is counter based. So we'll discuss them one by one. So what is mux based microprogram? So it's not very different from this, but we combine this x and y to single variable, let's say n. Okay, so because at a single point, uh, okay, so let me explain it another way. No, okay, we have to combine them both in a single variable n. Now as you can see here, it's no problem, because at a given time, in a given state, the next state is dependent on only one of the variables. So we can just code it in here that it is dependent on x at this state and it is dependent on y on this state. Let's say we have a state k, right? And it's dependent on both x and y here, x and y. And you have 4 output lines, right? 0 0, 0 1, 1 0 1, right? This is the total possibility. Now what we do here is we convert this to something like this. We have a state k here as usual. Okay, it depends on just x now. Okay, if x is true or x is false. Okay, then again we check y. We have to check y here. Instead of that, we put a pseudo state here. We put in a pseudo state will be equal to again k. It's still k. Output, if it's output 1, it will also have output 1. No, sorry, it won't have any output. I'm sorry, let's say it is k dash. It won't have any output because it's not yet activated, right? The output is not yet activated. And after that we'll check y. Here we'll check y. Similarly, if it's 0, similarly if it's 1, again we'll keep a dummy state k dash. You have to give these numbers, right? If it's 0 state 0 0, I'll call it state 0 1 and this state 0 1 0, right? And again I'll check for y. You may think that introducing the states may increase the complexity, but we'll see that it actually reduces it. Uh, Now y. So y is 0 or 1. It's 0 or 1. So if x is 1 1, we'll go. We have this 1 1 line, and this is x and y. This is 0 1 line. This is 0. Okay, this one will be 1 0 line. This is 1 0 line. This is 0 1 line, and this is 0 0 line. We still have 4 lines equivalent to this 4 lines, but we have uh, uh, expanded this thing to this thing. Now why do we do that? To make every state uh, dependent on only one variable, x or y, either x or either y. Here it was, you can do this for n number of states, right? uh, After each step you have to add a pseudo state here, so that we can reduce this x and y into a single variable. Let's say n. This is test variable n, either x or either y. Now how will this affect us? Let's erase this thing. Okay, okay, let's erase this. Now let's make a state table for this thing right here. Okay, now how would we make a state table? So uh, I'll make a test variable n, which will be equal to 0. Then the variable we are using is x. If it is equal to y, if it is equal to 1, then the variable we are using is y. Cool. So and by default, if it's not using any of the states, we'll just say that it depends on x. Okay, and okay, it just depends on x, but like for default it depends on n0 for that. So now how will you do that? Let's say we have current state. Again, you don't need to write this, I'm just writing it for our convenience. The next state, the next thing we'll have is n, of course, n. Then depending on n, whether it's true or whether it's false, we'll have two different things, right? So I'll have a current state, sorry, a true state, a true address, and a false address, right? True address means if the variable x, if the variable which this n selects, either x or either y, is true, then we go to this address. If it's false, we go to this address. Address means the state address, the A and B. We are talking about A and B here, the state address. So I'll just make it as decimal. I'll just write it as decimal 0, 1, 2, and 3. Okay, we'll use decimal here. We'll convert it into binary while analyzing it. So let's say the current state is P. Now N here is 0. Obviously, right? It's 0 because it depends on X only. It does not depend on Y. If N is 0 here, what is the true state? What is the true address? If X is true, we go to address number 1. If X is true, we go to address number 1. If X is false, we go back to address number 0. We go back to address number 0. Right? And what will be the output? What is the output here? Output is O1. Let us just call it output again. It's O1. Okay. Okay, I'll make this current address as 0. Current address is 0. Okay, and N will be 0 for that. Now if the current address is 1, the current address is 1, what is N? We don't have anything, so we default to 0. We default to 0, and because we don't have anything which is just dependent on the true address and false address would be same. Both would be same. So what is true address and what is false address here? Both would be 2, because after 1 we directly go to the second state, right? First state, we go to second state number 2, and the output is O2. Simple. Now current state is, let's say, 2. Current state is 2. The N would be 1 here, right? Because it's the variable is Y. It does not depend on X, so it depends on Y. N will be 1 here. The true address for 1 would be 1 again. State number 1, Q. And for false address, it will be state S, that is 3. And the output would be O3. And you go here, state 3. So it does not depend on anything, and we can keep anything. We'll keep it as 0 default. True address and false address both will be same. It goes to 0. State P is 0, so go to 0, and output is O3 again. So now you can see that how we have reduced it completely. So now how can we design this? So let us design this. We have PROM, EPROM, or some memory element. What is the input you can give? The current state, that will be 2 lines, 2 bits wide, right? Because we have 0, 1, 2, 3, we can represent it in 2 bits. N will be single bit. True address would be, again, because it is address, we have 2 bits. False address is 2 bits. Output is 3 bits, right? So what we have to give is current address, just current address, right? It will take input as just current address, nothing else, right? Because, and also the variable here, so it will take input as current address, just 2 bits, and we'll have output as an output N, and we'll have X and Y here. Okay, we can keep a mux here, 2:1 mux. This will be 2:1, X and Y, and we'll have our variable here. Okay, this is N. Now a true address and false address. I'll have true address, I'll have false address. I can give it in a 4:2 mux. Oh, sorry, 4:1 mux right here. If I give this as input, This is true address, this is false address. I can make a 4:2 mux, 2, and I'll have two output lines. 4:2 mux is a relatively new concept. It's nothing but just two 2:1 muxes parallel. Okay, so I'll have true address first bit, 0th bit, and true address first bit, and I'll have false address 0 bit here, false address 1 bit here. So I'll get output as the address bit 0 and address bit 1 here, and I'll give them both the same input, right? Single. So I can get it. Okay, I hope you understand this 4:2 mux concept. So we get the address lines here, right? And again, as we have this address lines here, we give it into a we give it to two flip-flops. We have two flip-flops because we have four states, and they give this back. So the input address lines are 2 bits wide, and output is 1. Oh sorry, we have more outputs. 3 here, 2 here, 2 here, and 1 here. So it's 8 bits. Right, so it's 2 to the 2. This means we have 4 address lines. We have 4 address lines, and we have 8 bits. So multiply with 8. We have 32 bits in total. As you can see, we have reduced our complexity from 80 bits down to 32 bits. Impressive. So next, and also just with you have to program this only 4 times because we have only 4 address lines. Okay, and this right here, this table, this is called microcode. This is called microcode here. This is microcode of this ASM. Microcode for this ASM in mux based microcode. Okay. Now let us discuss what is counter based microcode. I'll select this and I will copy this thing right here. Okay, I have copied the ASM. Now we just need a different numbering here. Let me introduce you the counter based. What is actually counter based ASM? So the idea here is that uh, if we are on a state 0, we give it to counter. We have a counter here. We are on state 0, and we have a different variable. That variable is let's say to jump, and if to jump is false, the counter increments this by 1. We go to state from state 0 to state 1, and state 1 to state 2, state 2 to state 3, state 3 to state 0 again. It's a mod 3 counter. Okay, if if to jump is true, if it's high, let's say if it's true, then like it's like a load signal in the up down counters. If the load signal is true, then we will give it a we'll give it an address here. We'll give it an address, let's say 2. Then it will start counting from 2. In the next thing, in the next clock cycle, if this becomes false again, that 2 will be incremented to 3. Okay, this is the basic idea behind the counter based microprogramming. So you would understand why we are doing this, but just for the sake of it, I'll tell you. On every variable, again, for microcode we have to do this. You need this again, like every state should be dependent on only one variable, either x or either y. So we already have this in the ASM. If we don't have this, we expand with the technique we discussed earlier. Okay, so if you have this ASM, so what you have to do is just assign a state. Let me use a different color pen. Just assign a state, just assign a uh, address to a state. Let's say this is address 0. If this is address 0, then for every variable, either of them, either true or false, one of them should be the next state. What is the next of 0? Should be 1. Okay, one of them should be 1. So let's say the true, because this is false, so it is jumping back to 0, right? If we give this to a counter and x becomes false, then counter should not increment. And if it's true, the counter would increment 0 to the 1. So the state, let's say we give this number 1. I'm giving this 0, this is 1. Okay, I don't like that color. Okay, so let's say this is 0 and this is 1. Okay, this is called sequential address. This is sequential address. For false, we are we have a jump address. Okay, we have a sequential address and a jump address here. There we in previous one we had a true address and a false address. Here we have a sequential address and a jump address. Sequential address is just the next number in the word counter. Okay, now because we have 1 here, so next can be true or can be false, right? So we prefer if a state does not depend on any variable, we prefer that it is not sequential. We prefer that the next state address is not sequential. So if it's 1, we give it a 3. You can't give it 2. You can give it 2, but after 1 we have 2. We do not prefer it, we prefer a jump address here always. Okay, so you have 0, 1 and a 3. So after 3, because it is in y, we have y here, it should go back to 1. This is a jump address, so s is supposed to be sequential, but we have only thing we have left is 2. So this order cannot be possible. This order is not possible. We cannot give this order of addresses. We cannot assign this order of addresses to these states. Now let's start over. You have to do this every time when you are writing microcode for, you are building a microcode for ASM in counter based approach. Okay, so let's say p here is 1. If p is 1, the false is automatically jump, so the true one should be sequential. We have 2 here. After 2, we prefer a jump address here, so it will be 0, right? So 0 to 2. Okay, I guess we have no other choice than giving it a jump to. Okay, let's say in the previous example only we'll give it 0. If we give it 1, and instead of jump address we give it there as a sequential only 2. We see that for the y's, when y is true, we prefer jump here, but you can also give sequential address, it's no problem. We prefer jump address rather, because sequential addressing is difficult to come up with, right? So okay, so if 2, if we present it with 2, you check y. If y is true, then we have a jump address, because 2 to 1, if we give 2 to a counter, it will go to 3, right? So if it's false, we have a sequential address. So now you have to check for every variable, do you have one sequential, uh, and one uh, jump address or not? For x, if x is false, we have a jump address 0 to 0. Okay, 0 to 0 is jump. For if x is true, we have 0 to 1. 0 to 1 is sequential. uh, we don't have any variable here. The next variable is y. If the variable is y, one address true, the true address is 2 to 1. The two address is 2 to 1, that will be jump. And the false address is 2 to 3, that is sequential. So one jump, one sequential, one jump, one sequential, we are ready to go. Now, as you might have here, we have a different approach for n, the test variable, which takes input as x and y. Here n will have three possible states, either x, y, and one another that would be uh, always tied to high. That would be n of 0, this is n of 0, n of 1, n of 2. Okay, three states. N of 1 is all, n of 0 is always tied to high. Okay, we'll discuss this why in a while. Okay, now it would be the similar as this. We'll write current address. Current address. Now, as we discussed earlier, we need a, a true false bit, right? We need a okay, encounter. Where did we discuss? Okay. So for a counter, we need a load bit, right? Bit tells it when to load the address which is given to it. So uh, let the load bit be true if the jump address is true. Like we have to load only if we want to give jump address, right? So jump address. If it's a jump address, we have to give load true. Now, how do you know if it's a jump address or not? Uh, see, uh, for x, if x is false, if n of 1 is false, if n of 1 is false, for n of 1 we need false. So jump address is true. For n of 3, if n of 3 is true, jump address is true. Now n of 1, we know n of 1 is always true. And the only thing we have here, the only thing next, uh, like we, even though 1 to 2 is a sequential address, we use it as a jump address. Why? Because we need, because if somewhere else in the ASM, there is another state transition which does not depend on uh, uh, a variable, like s to uh, p, again s to p. Here luckily we have both of them as sequential addresses, right? Like q to r is also sequential, and s to p is also sequential, because 3 to 0 is sequential in the counter. But if we have a clash here, like if we had 1 to 3 here, or let's say this is 4 and this is 0. So if this was jump and this was if this was jump and this was sequential, how would you encode it here? How would you encode it here? Like here we have written for a variable x, if it's false we have to jump. For a variable y, if it's true we have to jump. For a different variable, this is null variable, we have created this variable. If it does not depend on any of them, right? If it does not depend on any of the variable, the state transition does not depend on any of variable, we'll use this n of 0. We'll use this, and this should be always similar, right? Either if it's true, if we keep it as true, either either it should always jump, or either it should always be sequential. So it will be clear once we do an example here. Let's say we have n, and just we only need jump address here. We don't need a sequential address, because sequential address we can calculate by the current address, just add one. Okay, and we want output here, right? So also we need the load bit. Okay, we need jump address here and load bit. We call the load bit as a true false bit. It's called as true false bit. It's the load in the counter. Okay, the current address is 0. We if we only need to specify, let's we only need to specify the n if it's okay, we need to specify n, right? This n would be 1 here. N would be 1 here because we need x. For x, n is 1. N is 1. You go back, uh, and true false bit, the load bit is false. If x is false, you jump to 0. If x is true, you just go forward. If x is true, you don't need to specify here, right? False, I'll write it as 0. If x is low, you jump to 0. And the output would be O1. And if x is true, if x is true, true false is true, then you don't jump, you just go with your life. Okay, and if current address is 1, now here comes the fun part. If n is 0, okay, if we have n 0, how do you check? We generally use it, we generally uh, do like, if this is false and we have true false bit, right? If x is false, you go to x value, this x, it's x value, and it's the true false bit which will come out from the PROM. You do this implicit operation. It will be high only when x and test bit, true false bit, are true. If both of them are equal, then only this will become high. Okay, so you can check if the two bits are true together. So if n is 0, we have the value 1. Okay, we jump only if it's true, because this value and this value should be equal. Like this is the test bit, right? Or true false bit. This is the true false bit, and this is the value. If these both are equal, then we jump. Okay, now true false bit should be 1, so that if n is 0, you go to, we have this value, n of 0 is 1, and 1 x naught, okay, it's implicit operator, this is x nand, 1 x nand with 1, we get 1. So you jump to 2. Even though this is sequential, we write it as a jump address. Okay, and you get the output O2. If your current address is 2, current address is 2, uh, your n should be 3, because it depends on y. It depends on y, n should be 3. And if y is false, if y is false, you sequential. If y is true, you go to jump address. If y is true, you go to jump address. Y is true, you go to jump address. What is jump address? 1. And output is O3. And with O3, if you're at 3, no matter, because it does not depend on variable, no matter what, you use 0, and you have to jump only. So you go with true bit true, test bit true, true false bit true, and jump address is 0, and output is O3 again. Now how do you design this? How do you design this? We use a PROM. Okay, and we need a counter. We need a counter. Now of course the PROM will get current address. Current address, uh, right, it will be 2 bits. N would be 2 bits again here, because we have 3, so n would be 2 bits. The LDA, or the load bit, here we have a load bit, right? Load bit, that would be a single bit. Jump address would be 2 bits. Output would be again 3 bits. Cool. So we have n coming out of here, right? N coming out of here, 2 bits. 2 select lines. You will again have a mux here. This, the first will be tied to true, of course. We use this table here, and first one will be tied to true, second one will be x, third one would be y. If there are more variables, so on. Oh, okay. Next would be the true false bit. We will have a true false bit here, and we'll check if both are equal by this implicit x NAND operator. Go here, we give it to load bit. This will be high only if these both are equal. If these both are equal, you take out a jump address. We'll give this jump address. If these both are equal, the jump address will have it here, right? And what else? We'll have a clock, system clock, and what else? The outputs, right? 3 outputs. We'll have 1, 2, 3, 4, 5, 6, 7, 8 again. This will be 2 lines. These are again 8 lines. 2 is to 8. Similar to the previous one, 2 is to 8. We'll again have 32 bits in the PROM, which is significantly less than the 80 bits from our conventional design. And we have a counter here. We'll have 2 flip-flops again for saving the state, and this port will also have a clock. Same clock here. And these are outputs. The outputs and the x's, x and y's, both will be coming from an sequence. Both will come from a combinational circuit, right? Combinational circuits. Okay. So this is the, and again, this is the microcode for counter-based circuits. This is the microcode for counter-based circuits, and this is how you design them. That's it. Thanks for watching.